Your heart attack risk is highest before you've had lunch, not because of what you eat, because of what your body does while you sleep to get ready for morning. This isn't a fringe finding. The morning peak in myocardial infarction, the window between roughly 6 a.m. and noon, has been documented across decades of epidemiological data. The risk isn't uniformly elevated, it spikes. And the spike is mechanistic, not coincidental. To understand why, you need to follow 3 separate systems inside your body, all running their own circadian programs, all converging on the same dangerous moment. Here's a question worth answering in the comments before we go further. Have you ever woken up in the night with chest discomfort, or noticed that the cardiovascular events in people you know tended to happen in the morning? Yes or no, or a story if you have one. The pattern keeps coming up in these conversations and it's worth mapping. Start with the simplest version. Your heart is a pump. It sits inside 3 coronary arteries, the left anterior descending, the left circumflex, and the right coronary artery that wrap around it and feed it blood. Any one of those arteries can develop a plaque, a soft lipid-rich deposit under the inner wall, covered by a thin fibrous cap. The cap is structural. It holds, until it doesn't. And when it ruptures, blood enters the plaque, the clotting cascade activates, and within minutes to hours, the artery can block entirely. That blockage is a heart attack. The question isn't only whether you have plaques, it's whether the conditions exist to make one rupture on any given morning. Those conditions are built overnight. The first system to understand is the autonomic nervous system, the part of your nervous system that runs automatically, below conscious awareness. It has 2 modes, the parasympathetic branch, which governs rest and recovery, and the sympathetic branch, which governs readiness and threat response. During sleep, parasympathetic tone dominates. Your heart rate drops, your blood pressure falls, your blood vessels relax, the cardiovascular system is genuinely at rest. Then, somewhere between 90 minutes and an hour before you open your eyes, the system shifts. The suprachiasmatic nucleus, the brain's master circadian clock, a small cluster of neurons sitting just above where the optic nerves cross, sending signals. Cortisol starts rising. The sympathetic nervous system begins its handover from parasympathetic dominance. By the time you actually wake, norepinephrine and epinephrine, adrenaline, and its quieter chemical sibling are surging. Research measuring catecholamine levels in people upon arising and standing found norepinephrine increase by 189% and epinephrine by 130% compared to lying still. When you stand up, the surge amplifies further as the body compensates for gravity pulling blood toward your legs. This is the cortisol awakening response, a sharp 50 to 75% spike in cortisol occurring in the first 30 to 45 minutes after waking. It's not a stress response in the pathological sense, it's a preparation sequence. The body is mobilizing resources, activating the cardiovascular system, priming you for the demands of the active phase. In an ancestral context, this made sense. You needed to be alert, mobile, and physiologically ready, fast. In a body with atherosclerotic plaques, that same preparation sequence becomes the problem. The sympathetic surge does several things simultaneously. Heart rate climbs. Blood pressure rises. The systolic morning surge is typically in the range of 15 millimeters of mercury above the sleeping nadir. Coronary artery tone increases, meaning the vessels themselves constrict slightly. The heart is now working harder, against narrower vessels at higher pressure, delivering more oxygen demand to tissue that may already have compromised supply. Imagine squeezing water through a kinked hose with more force. The point of least structural integrity takes the stress. That point is the fibrous cap over a vulnerable plaque. The fibrous cap is a roof. Under it sits a lipid-rich inflammatory necrotic core. Macrophages that consume too much oxidized cholesterol died and left behind a pool of thrombogenic debris. The cap's job is to isolate that debris from the bloodstream. But the cap has tensile limits and circumferential wall stress, governed by Laplace's law, which relates pressure, vessel radius, and wall tension, rises with blood pressure. The morning pressure surge doesn't just challenge already narrowed vessels. It increases mechanical stress directly on any plaque that's sitting in a moderately sized lumen. Not severely stenotic plaques, which have already remodeled and often prompted collateral circulation. The vulnerable ones. The plaques causing 40 or 50% narrowing that nobody knew were there because they weren't yet causing symptoms. 3-vessel intravascular ultrasound studies have found that plaque ruptures in the left anterior descending artery cluster heavily in the proximal segment, within 10 to 40 millimeters of the vessel's origin. The iliad supplies the anterior wall and most of the septum of the left ventricle. It's the vessel cardiologists call the widowmaker, which is, as clinical nicknames go, admirably direct. Here's what I find strange every single time I think about it. The plaque that kills someone on a Tuesday morning at 7 a.m. may have been sitting undisturbed for years. The blood pressure that ruptures it may only be 15 points higher than it was at midnight. And the whole catastrophe hinges on a timing signal written into the genome. Not into the plaque, not into the blood pressure directly, but into the clock. Now add the second system. Your blood isn't a passive fluid. Its clotting tendency, its willingness to form a thrombus, follows its own circadian program. And that program peaks in the morning, independent of anything you do behaviorally. Plasminogen activator inhibitor 1, known as I1, is the primary brake on fibrinolysis, the process by which your body dissolves clots. When PAI1 is high, clot-dissolving machinery runs slowly. Small clots that would normally be cleared quickly instead persist and grow. A study published in Blood, using a forced-desynchrony protocol to isolate the body's internal clock from all behavioral and environmental cues, found a robust circadian rhythm in circulating PAI1, peaking at approximately 6:30 a.m. The rhythm driven by the internal clock alone was 8 times larger than the PAI1 changes caused by physical stresses like standing or cycling. The body wasn't responding to what participants were doing. It was running a preset program. The word for what results from elevated PAI1 is hypofibrinolysis. The accurate description is, your body has turned down the drain. Meanwhile, platelets, the small cell fragments that form the initial plug in any clot, are also following a morning program. A separate controlled study on endogenous circadian platelet activation found that 3 key surface markers of platelet readiness, including activated GPIIb-IIIa, the final common pathway through which platelets aggregate, all peak at around 9 a.m., independently of sleep, posture, or activity. The body is making its platelets stickier on a schedule. On top of this, hemoconcentration. 8 hours of no fluid intake makes the blood thicker. Hematocrit, the fraction of blood volume occupied by red cells, increases with dehydration. Whole blood platelet aggregation in response to collagen stimulus increased by 71% in people upon arising and standing. Part of that increase was directly mimicked in laboratory conditions simply by replicating the hemoconcentration alone. The blood you wake up with is measurably different from the blood you went to sleep with. Thicker, stickier, less inclined to dissolve an emerging clot. Now the geometry matters. 3 coronary arteries, different anatomy, different susceptibility to the morning surge. The right coronary artery carries blood through the entire cardiac cycle, systole and diastole, because the right ventricle's contraction doesn't compress its intramural vessels the way the left ventricle does. The left anterior descending, feeding the high-demand left ventricle, gets squeezed shut during systole and relies on diastolic flow. When sympathetic tone rises and heart rate climbs, diastolic time shortens. Each heartbeat is faster, leaving less time in the resting phase when the lady actually fills. The left anterior descending is therefore doubly penalized. Its wall stress rises with blood pressure and its perfusion window narrows with heart rate. The proximal LAD, where most plaque ruptures cluster, is experiencing maximum mechanical loading at the same moment its oxygen delivery is most constrained. Honestly, I spent a week once reading nothing but papers on mechanisms like this. Systems that run in parallel invisible, each one plausible in isolation, genuinely alarming in combination. This was one of those weeks. The cardiovascular morning convergence doesn't read like a design flaw. It reads like a feature that became a vulnerability the moment plaques entered the picture. The third system is the one researchers are still actively working on. A paper published in Nature in May 2025 identified that BMAL1, a core circadian transcription factor that drives the body's internal clock, forms a previously unknown molecular partnership with hypoxia-inducible factor 2 alpha, called HIF2A, in heart muscle cells. This partnership, active in a diurnal pattern, appears to govern how much damage heart muscle sustains when blood supply is cut off. In the morning, this BMAL1 HIF2A complex is more active. And in clinical data, morning-onset myocardial infarctions consistently produce larger infarct sizes and worse outcomes than those occurring in the afternoon or evening. The same blockage in the same vessel in the same person, but arrived at 8 a.m. instead of 8 p.m., kills more tissue. The clock doesn't just set the timing of the event. It determines how bad it is. That detail is preliminary. The 2025 Nature paper is the clearest molecular explanation yet identified, but the clinical translation, Whether you can meaningfully intervene at the level of BMAL1 HIF2A is not yet established. The epidemiological pattern is solid. The molecular mechanism is new. This is where the gap lives. Three systems, the autonomic surge, the prothrombotic cascade, the circadian injury amplifier, are well documented individually. Their convergence as a unified picture explaining morning cardiovascular mortality has taken decades to assemble, and the third component was only characterized this year. There are likely interactions between these systems we haven't fully mapped. What's clear is the direction. Here's the thing about the morning peak that most prevention advice misses entirely. The risk isn't just about whether the event happens, it's about whether the event is survivable. Morning infarctions are larger. They're more likely to involve the proximal LAD. They happen in bodies that have just come off 8 hours of physiological preparation for the event. The window from 6 a.m. to noon is not simply when the event occurs. It's when the event occurs in the worst possible physiological context. So what does the mechanism actually point toward? In the short term, this morning, the morning after this one, the transition from sleeping to standing is not neutral. The abrupt posture change from horizontal to vertical triggers the orthostatic component of the sympathetic surge. Sitting at the edge of the bed for a few minutes before standing isn't about being careful in a vague wellness sense. It's about not compressing the transition from parasympathetic to sympathetic dominance into 30 seconds. The body's pressure regulation systems, baroreflexes, the renin-angiotensin-aldosterone axis need a moment to catch up. Giving them that moment isn't dramatic. It's just not actively forcing the surge faster than it was going to happen anyway. Hydration matters in the same purely mechanical way. Blood viscosity increases overnight. Drinking water before anything else reduces hemoconcentration, brings platelet aggregability closer to baseline. This isn't a detox claim, it's hydraulics. Over days and weeks, the mechanism responds to anything that flattens the sympathetic morning surge. Regular aerobic exercise reduces resting sympathetic tone, which means the morning handover starts from a lower baseline. Sleep quality matters directly. Disrupted sleep amplifies the cortisol awakening response and blunts the normal nocturnal blood pressure dip, which means you arrive at morning with less recovery and a steeper ascent. The research on short sleep and cardiovascular risk runs through several of these pathways simultaneously. On the question of medication timing, the picture is genuinely still being assembled. The chronotherapy hypothesis, that aspirin taken at night achieves peak platelet inhibition during the high-risk morning hours rather than peaking mid-morning and declining into the afternoon, is biologically coherent. Studies have shown that bedtime aspirin's dosing reduces morning platelet reactivity compared to morning dosing. But large randomized trials with cardiovascular events as the primary outcome haven't been completed yet. The biomarker evidence is there. The clinical outcome evidence is not at scale. This is a conversation worth having with a cardiologist if you're on anti-platelet therapy, not something to change unilaterally. The mechanism doesn't read the clock on your wall. It reads the state of your autonomic nervous system, the viscosity of your blood, and the structural integrity of any plaque your immune system has been quietly managing for years. Those are the inputs it responds to. Return to the simplest version. Your body treats the transition from sleep to waking as a physiological event requiring preparation. Blood pressure up, platelets primed, clot-clearing machinery slowed, coronary tone increased. For most people, most mornings, the system works as intended. For anyone carrying a vulnerable plaque, and most people don't know they are, those same preparatory changes are the conditions under which rupture is most likely. The morning risk isn't bad luck. It's the same system that kept your ancestors ready, running in a body that has accumulated something those ancestors rarely lived long enough to accumulate. Tell me in the comments, does knowing the mechanism change how you think about your mornings? Not looking for routine descriptions. I want to know if this lands differently when you know what's actually happening in the hours before you get up. When you wake up tomorrow, the first thing your body will do is prepare itself for the day. The second thing, if you don't rush it, is survive that preparation.